Okay, this is 6.2 example 4. Students do find radians a little tricky, and part of that is if I told you that this was the sine of 15 degrees, you would probably immediately recognize that you could write 15 degrees as 45 minus 30, because that is 15. In radians, that's a little harder to see. What I recommend students do is they write out the radians that we know. So we have 60 degrees, 45 degrees, and then finally 30 degrees. And if we want to find out how to add and subtract these to get pi over 12, it's very useful to write these as 12s. Well, pi over 3 corresponds with 4 pi over 12. Pi over 4 is 3 pi over 12, and pi over 6 is 2 pi over 12. So the real question becomes, which one do we want to use? We could say 4 pi over 12 minus 3 pi over 12 is 1 pi over 12, or we could say 3 pi over 12 minus 2 pi over 12 is 1 pi over 12. Now, what's annoying about this, or maybe not annoying, but it doesn't actually matter. It makes no difference as long as the sum or difference does add to the original angle given. I really don't care, but I'm just going to use the first two I see. So I'm going to say that the sine of pi over 12 can be written as the sine of 4 pi over 12 minus 3 pi over 12. Now, you don't have to write it like that, but I like that kind of, little verification. Is 4 pi over 12 minus 3 pi over 12 1 pi over 12? And it definitely is. They have a common denominator, and 4 pi minus 3 pi is 1 pi. So what I'm going to do now, though, is I'm going to rewrite that using the angles as they would appear on the unit circle, because that's really what's going to be our next step here. And I shouldn't say next step. We first have to take that difference and write it out using the formula on our formula sheet. And I'm going to write it above just to make sure you see exactly what's happening. And the sine of angle A minus B is equal to the sine of A times the cos of B minus the cos of A times the sine of B. Now, for this particular question, A is pi over 3 and B is pi over 4. So the sine of pi over 3 minus pi over 4 is the sine of pi over 3 times the sine, not the sine, sorry, the cos of pi over 4 minus the cos of pi over 3 times the sine of pi over 4. And then what the question becomes after this is just evaluating it. And it really is why we push that unit circle so much, because if this is tricky to evaluate, you have to go back and gain a little more mastery of the unit circle, because this is going to come up again and again and again. Well, the sine of pi over 3 is root 3 over 2. The cos of pi over 4 is root 2 over 2. The cos of pi over 3 is 1/2. And the sine of pi over 4 is root 2 over 2. What I can do now is I can simplify those expressions. Root 3 times root 2 is root 6. 2 times 2 is 4. 1 times root 2 is root 2. And 2 times 2 is 4. Radicals cannot be added or subtracted unless they have the same radicand. Root 6 and root 2 do not. So we would have to simply combine these and say root 6 minus root 2 all divided by 4. And that is what the sine, now it is pi over 3 minus pi over 4. Remember back at the start of the question, we were really trying to find out what the sine of pi over 12 is. Now, we do have to do a part B, but I want to show you how easy it is to verify this. What I would do on my calculator, and I would have to be in radian mode because pi over 12 is in radians, but I could just check the sine of pi over 12 and see that that's equal to, some ugly decimal. And then what I would have to do is check the square root of 6 minus the square root of 2 divided by 4, and we see that we get the exact same decimal. That's a nice, quick, easy way to verify that you've done this correctly. When we ask you these types of questions, we are going to ask for exact form, because we know you could just use your calculator for the sine of pi over 12 really, really quickly. All right, sine and cos aren't as bad just because they're double angle identities, or sum and difference identities don't introduce a fraction. Tan, on the other hand, is a little bit trickier for sure, and it definitely involves a lot more algebra as we go through it. But first things first, I'm going to write these out: 35 degrees, 45 degrees, and 60 degrees. Looking at this list, hopefully it's not too bad to recognize that 105 degrees is the sum of 45 and 60. If you are given a question that involves tan, if you can use 45 degrees, make sure you do, because the tan of 45 degrees is 1. So it's very easy to use, whereas the tan of 30 degrees and 60 degrees is going to be a little bit harder. To try to make that a little bit easier, I'm just going to put a big P here. And if we look at the point for these angles, we really only have to worry about the bottom two. So the point at 45 on the unit circle is root 2 over 2 comma root 2 over 2. The point at 60, though, is 1/2 comma root 3 over 2. And the reason why this is so important is we're going to end up taking the tan of these angles. So before we do anything, I'm going to write down here that the tan of 45 degrees is 1, but the tan of 60 degrees is the y coordinate divided by the x coordinate, which works out to just root 3. Now, knowing what the tan of 60 is very, very useful, because on our formula sheet, we have that the tan of a plus b is equal to, and this one's a bit of a doozy, tan a plus tan b, all divided by 1 plus tan a times tan b. Now, for our particular question, I'm going to do two things here. I'm going to say that the tan of 105 degrees is equal to the tan of 45 degrees plus 60 degrees. And then what I'm going to do, and I'm just going to kind of draw it as an arrow here, that the tan of 45 plus 60 is this, except A is 45 degrees and B is 60 degrees in this context. So that's going to be the tan of 45 degrees plus the tan of 60 degrees, all divided by 1 plus the tan of 45 times the tan of 60. And this is why tan is complex, is because now we have to actually evaluate tan 45 plus tan 60 all over that expression on the bottom. But like most things in math, take it piece by piece, right? The first thing we're going to do is we know, and we kind of lost them here, sorry, I'll write them again, that the tan of 45 degrees is 1, and the tan of 60 degrees is root 3, which means anywhere I see tan 60 or tan 45, I can replace it with what they are equal to. So we are going to have, and I'm going to write it like this, that the tan of 105 is equal to, and now I'm going to plug those values into my expression. So that's going to be 1 plus root 3 in the numerator. In the denominator, I'm going to have 1 plus 1 times root 3. And so what I have, oh, you know what? I messed up the identity. Sorry about this. This should actually be a minus. And that is definitely on me. That's the problem with looking at these identities all together. That definitely is a little bit of an oversight. So on the bottom here, we're going to have 1 minus root 3. Now, I should, I guess, make a quick mention as to how I knew I made a mistake. If I left that as 1 plus root 3 over 1 plus root 3, I'm going to get 1. The tan of 105 degrees cannot be 1. It doesn't have a reference angle of 45, and it isn't 45 degrees, so I knew that it had to be more complex than that. It is not a bad idea to, right at the beginning, get that decimal value for what it's equal to. So if I go to degree mode here, I can type in the tan of 105, and we can pretty clearly see that we expect to get a pretty ugly looking decimal. Now, the way that we get that decimal is by cleaning up the expression we have. So I have 1 plus root 3 divided by 1 minus root 3. You've been taught for a couple years now that we can't leave a radical in the denominator. Because it's two terms, I'm going to introduce its conjugate, and I'm going to multiply the numerator and denominator by that. Now, when I multiply the denominator is 1 minus root 3 times 1 plus root 3. That's a difference of squares. And what I get on the denominator is 1 minus 3. So that's a squared minus b squared, respectively. The numerator is tricky. You have to use the distributive property. I'm going to show that here. So 1 times 1 is 1, plus 1 times root 3 is root 3. Then I have root 3 times 1, which is root 3. And then lastly, I have root 3 times root 3, which is 3. So from here, we can start to combine our like terms. And we're going to be able to say that the tan of 105 degrees is equal to 4 plus 2 root 3 divided by negative 2. We can simplify that. That becomes negative 2 minus root 3. And it's never a bad idea to check. I have this in the calculator already. I put in that the tan of 105 was equal to negative 3.73. Well, if I put in negative 2 minus root 3, I get that exact same decimal. Please do verify your answers when you're doing these. I mean, you saw how easy it was to make a mistake when you're reading that identity off the formula sheet. There is, unfortunately, plenty of room for error in these types of questions. Okay, I'll put that assignment up. I will give you a modified assignment for the kind of the digital assessment there. Good luck, and please do email if you have any questions.